back, CHEM200L. Hope you and your family are all well. This is day one back at lab. As usual, you come in, we've got announcements. I know it's going to take some time getting back, but we'll do our best to get up to speed and get back going with the routine. Speaking of routines, your post-lab due for experiment 2, I know that's been a while ago now. That will be on Wednesday, March 25th. Let me know if you got questions about that. You can see pre-lab data observations for experiment 3. That's coming up on Wednesday next week. And then the post-lab is not till after spring break. Because we're now doing this class remotely, all of these deadlines will be at the end of the day, 11:59 p.m. I will have office hours for lab 12:30, so I'll send you an invitation. That'll be using Zoom, so we can go over questions. Monday, we can focus on activity 7, and so on. As usual, exam 1, take a week and a half to get back to you. So those are your announcements. Outline, this is what we're going to do today in these slides. The key is that this activity really prepares for the big experiment, experiment 7. So I know it's online, it's new, but it's really important to have these skills and understanding down. We'll talk about serial dilution, independent concentration. The SpectraVis Plus is an important equipment that you'll use or be shown how to use in this lab. And then we'll continue with graphs. Please note there's 2 graphs for each method. So if there's 2 methods, then we obviously have 4 graphs, okay? You'll have 2 graphs that are absorbance versus wavelength, and then you'll have 2 graphs of absorbance versus concentration. You can use either Logger Pro or Excel to graph. It just depends on what you have and what you prefer. Remember, we're going to be doing a best fit line, and you've seen this before. In Logger Pro, the best fit uses the terminology correlation. Excel uses the term R squared. Those are close to 1. That shows you have a good linear fit. And then the rest of this time will be activity 7, and that will be on lab archives. I'll show you where that's at. So the schedule, Monday, activity 7, Wednesday, experiment 3, and then spring break as scheduled. Serial dilution. So you may recall this equation, and you maybe even use this equation a lot. M1V1 equals M2V2. So that's the molarity, that's the volume, and that equals molarity times volume. Well, let's take a look at that real quick. If we have molarity, that's moles over liters, and if we multiply that by liters, we get moles. So really what this equation is saying is moles on the left equal moles on the right. So the reason we use this for dilution is because the moles of the solute doesn't change. What changes is the solvent added. Okay, so that's really key for serial dilution. So what it would look like if you were doing this in lab is, I'm just going to do a series of 3 just to show what we're doing. And let's call this a very basic 1 molar solution we're going to start with. So of course we'd start with the mass that we'd weighed out and put it in, and then we'd add the solvent, and we'd make a solution that's 1 molar. Okay, so serial dilution, we take some of this 1 molar solution and we put it in the next tube, and then we add more solvent. So remember, the moles on the left are staying constant. We're adding more solvent, so that's an increase in volume, then the molarity is diluting. So if we did this in half, that would cut that down to a 0.5 molar solution. And then of course you can continue this all the way. Here, do it again. And maybe you get to 0.25 molar. So you can see the highlights here of serial dilution. You weigh the mass once, and you add the solvent with pipettes, graduated cylinders, depends on the experiment. That's what you're adding to dilute to get your different solutions. So that's serial. Independent concentration is a little bit different. Okay, so we need the moles and the volume of the solution. And I'm just drawing easy test tubes, but again, it could be graduated cylinders. If you look at the activity, it could be volumetric flasks. In this case, you add mass to each one, and you add solvent to each one. So you can see you can make the same concentrations. You're just doing it in a different way. So this is independent, and the previous one was serial. What I like to do in this activity in person is ask students, which do they prefer? Because at experiment 7, it's going to be your choice. Do you make it through independent concentration? Do you make it through serial dilution? I want you to feel comfortable with both, and most usually do after this activity. After you make the solutions, then you want to check their absorbance. So that would be using the SpectraVis Plus. This is the equipment, the exact equipment that we have in lab. The steps, if you're going to use this, you'd warm it up. To calibrate, you'd use deionized water, which is really confusing because we call this a blank. So many times students put a cuvette in here with nothing in it, thinking it needs to be blank. Well, the terminology is a blank of whatever solvent you're using. So that would be deionized water. You've made all these solutions, then you measure low to high. How you do that is your cuvette is this plastic holder of the solution, and you want to rinse that because it's going to have some leftover liquid in it. Could be water, could be some unknown you don't know. So you just add a little bit of your sample, rinse, dump, rinse, dump, rinse, dump, and then you're ready to go and put it in the SpectraVis Plus. Cuvettes also are really sensitive. They have different sides. So if you have ridges, you don't have the ridges. You show the same side, clear side, towards this arrow over here every time. And you make sure and wipe off all fingerprints, anything like that. The video will show you more about that. Okay, so what are you going to do with this information? Well, you put in the SpectraVis Plus, and you'll get a plot, absorbance versus wavelength. And I'll show you those slides here shortly. What this looks like is a curve, absorbance versus wavelength, and that's collected from the SpectraVis Plus. So obviously you can't collect it yourself. I'll give you the data. But what I want you to see is that there are some regions that have higher absorbance and some that have lower absorbance. Experiment 3 talks about a region of the lambda max. What's the maximum wavelength? Sorry, what's the absorbance, the maximum absorbance at this wavelength? So you can see here that's pretty close to the peak. Maybe this is over here, but that's called the lambda max. Actually, in activity 7, you may study the lambda max for some solutions, or for our cases, because the concentrations are too high, you may study off to the right or to the left. These are called the shoulders. The reason we do this is the absorbance needs to be under 1. Okay, so if the lambda max is greater than 1, that's okay. We just go to the left, to the right, and now we record absorbances. So what your solutions are going to look like are they're going to have the same shape, but because they have different concentration, they have different heights. So that's absorbance versus wavelength collected. What you have to do now, you have to transfer this over, and you have to make a curve yourself of absorbance versus concentration. So the data is provided for you on Lab Archives. You can calculate the concentration of every solution, and then you'll give a plot here of some points that should show a linear relationship between absorbance and concentration. Please note, this absorbance That's at one wavelength. So if I choose this one over here, every solution is at that wavelength. What's the absorbance there? What's the absorbance there? What's the absorbance there? That's where that information comes from. Then put your best fit line here. So this is what you're doing. Remember, this you do, and this is provided. And I can show you shortly where that's at. So 2 graphs provided and 2 graphs created by you. All right, so now if I go to Lab Archives, you can see what our folders look like now. You go in here, you can see that there is Activity 7. Activity 7 has slides. That's what I'm recording right now. That'll go in here. Activity 7 has a nice video on what does it mean to make a calibration curve, use a SpectraViz, and so on. That's here. The data that I mentioned, this is the data that you need for serial dilution, calculate the concentrations. This is the data that you need for independent concentration, calculate the concentrations. And then I've got this SpectraViz data. Okay, so you see this is absorbance wavelength for serial dilution. It has 2 files, but they're the same thing. If you have LoggerPro, you can open up this LoggerPro file and analyze it yourself and pick the wavelength yourself. If you don't, that's okay. You just open up the image file and you can see that's the lambda max, that's the shoulder, and now these are the absorbances, the Y values, 0.787, 0.585, 0.397 for all the concentrations. Remember, the highest concentration has the highest absorbance, and it goes down from there. And you see they're all at the wavelength of 737. Then you go down, absorbance versus wavelength for independent concentrations, same thing. If you have LoggerPro, you can open it up. If you don't, if you just can open up the image file, then you can see this wavelength that's 817, and the highest absorbance is the highest concentration. So you can see that one is over 1, which isn't ideal, but you can go ahead and use the data provided. That is all I have for now. See me on Monday during office hours if you have questions.